In the post-war years, Detroit insisted that real performance required big engines, deep pockets, and factory-approved engineering. But one Southern California mechanic quietly proved them wrong. Barney Navarro, working with nothing more than a worn-out Flathead Ford, and a theory the experts dismissed, created a camshaft modification so strange and so effective that it embarrassed far more expensive cars, including Cadillacs. His trick challenged the industry's assumptions, exposed the limits of conventional wisdom, and forced racers to rethink what power actually meant. The controversy wasn't just the speed. It was how a backyard experiment beat corporate engineering. The Flathead Ford extinction event. Picture this. It is 1949. You are standing on the salt at Bonneville, surrounded by the smell of fuel and the sound of open headers. To the casual observer, this is the golden age of American hot rodding. But if you were paying attention, if you were really looking at what was happening under the hoods, you would realize you were witnessing a funeral. We clicked on this video because of a title that promised a simple cam trick. But let's be honest with each other right now. There is no such thing as a simple trick when you are fighting the laws of physics. What Barney Navarro did wasn't a trick. It was a scientifically calculated counteroffensive against an engine that should have been dead and buried. To understand why Navarro's work was so insane, you have to look at the Ford Flathead V8 without the nostalgia goggles. By the late 1940s, this thing was a dinosaur walking among mammals. It was built on what engineers call a side valve, or L-head architecture. That means the intake and exhaust valves weren't above the cylinder. They were sitting right there in the engine block, adjacent to the piston. Think about the path the air has to take in that engine. It has to go down through the carburetor, take a sharp 90-degree turn into the block, travel up past the valve, turn 90 degrees again to get over the cylinder wall, and then finally drop down into the combustion chamber. It is a torturous, circuitous route. It is like trying to run a full marathon while breathing exclusively through a coffee stirrer. The volumetric efficiency, which is just a fancy engineer way of saying how well an engine breathes, was absolutely terrible. The engine was suffocating itself. And it gets worse. Because the exhaust valves are also buried inside the engine block, all that superheated gas has to travel through the iron casting to get out. You are basically boiling the engine from the inside out. This 90-degree block was a thermal nightmare. You couldn't run high compression because the heat retention would cause pre-ignition or knocking, which would blow the engine apart. We are talking about compression ratios as low as 5:1. For 2 decades, mechanics just accepted that if you pushed a Flathead past 2200 RPM for too long, it was going to overheat, crack, or just give up. It was a foundation of limitation. Then came the meteor that wiped out the dinosaurs. 1949. General Motors dropped the bomb with the Cadillac 331 and the Oldsmobile Rocket 5.8. These were overhead valve engines. The difference was night and day. By positioning the valves directly above the pistons and utilizing cross-flow cylinder heads, the air went in one side and the exhaust went out the other. It was a straight shot. No turns, no mazes, no thermal soaking. These engines breathed freely. They could run higher compression and make power in a linear, predictable way that the Flathead simply could not match. The writing was on the wall immediately. You look at the Bonneville entry lists from that era, and you see an extinction event in real time. By the 1952 season, the overheads were already swarming. 4 Cadillacs, 2 Oldsmobiles, 5 Chryslers. Fast forward just 1 year to 1953, and the dominance was overwhelming. 17 Chryslers, 7 Cadillacs, 7 Oldsmobiles. The Flathead wasn't just losing, it was being erased. Sure, there were stopgaps, specialized conversion heads like the Outrun or the Tornado, but these were just band-aids on a broken leg. The engineering reality was harsh. The Cadillac gained power by just being efficient. The Flathead was structurally incapable of that efficiency. The scientist in the garage. In the late 1940s, the typical hot rodder was a scavenger. These were guys who built fast cars by digging through junkyards, swapping parts by trial and error, and usually fixing things with a sledgehammer and a prayer. Barney Navarro was not that guy. He was an anomaly. He was a rigorous, scientific engineer disguised as a mechanic. While his competitors were guessing, Navarro was calculating. Born in 1919, Navarro didn't just tinker, he studied. He spent his nights at Glendale High School, not goofing off, but in the machine shop, obsessively learning the trade of a tool and die maker. He served in the Army Air Corps, studying the high-stress components of aircraft engines. This background gave him a distinct advantage that money couldn't buy: precision. When he opened Navarro Racing Equipment in 1947, he wasn't outsourcing his manufacturing to some foundry across town. He was machining, finishing, and verifying his designs in-house. He adopted a philosophy from his high school science teacher that defined his entire career. There is nothing more fun than learning. That sounds like a nice motivational poster, but in the context of racing, it was a weapon. It meant Navarro treated every engine failure not as bad luck, but as a data point. He approached the Flathead Ford not as a V8 engine, but as a collection of thermal and fluid dynamic problems that needed to be solved. You can see this scientific rigor in his first major products. When he advertised in the very first issue of Hot Rod magazine in January 1948, he wasn't just selling shiny parts. He was selling solutions to the Flathead's inherent flaws. Take his aluminum cylinder heads. He didn't just cast them to look cool, he redesigned the combustion chambers to manage the heat that was killing these engines, allowing for efficiency that the iron stock heads could never achieve. But the real genius, the piece of metal that proves Navarro was playing a different game, was his 180-degree intake manifold. This wasn't just a pipe to dump gas into the engine. Navarro looked at the standard Ford manifold and realized it was a mess of uneven fuel distribution. Some cylinders ran rich, some ran lean, and power was left on the table. His solution was a dual-system design with a 180-degree firing event separation. He essentially split the engine in half diplomatically, ensuring that the carburetor pulses were perfectly timed to deliver an equal fuel charge to every single cylinder. But he didn't stop there. He looked at the geometry of the intake ports on the block and realized that the air was hitting a wall. So he designed the runners of his manifold to enter the block at a precise 45-degree angle. By doing this, the manifold became an effective extension of the intake port itself, smoothing out the airflow and reducing the turbulence that choked the stock engine. Think about the level of detail that requires. He wasn't just bolting a part on top of the engine, he was fundamentally altering the geometry of how the engine inhaled. He viewed the entire system as a thermodynamic equation. If the air couldn't get in efficiently, it didn't matter how much gas you dumped in. This 180-degree manifold was the proof that Navarro was operating on a higher plane of engineering reality. Engineering a system of violence. To reduce Barney Navarro's engineering masterpiece to a single camshaft is to misunderstand the fundamental physics of an internal combustion engine. A camshaft is just a machined stick of metal. If you shove a race cam into a stock engine, all you get is a rough idle and a car that won't drive. What Navarro built was not a modified stock engine. It was a fully integrated thermodynamic system, designed to exist in an environment of extreme hostility. He looked at the Flathead's deficiencies, the poor breathing, the heat, the heavy internal mass, and he systematically engineered a solution for each one. This was a total war against the engine's natural tendencies. It started with the breathing. We already established that the Flathead couldn't inhale enough air on its own to compete with the overhead valves. Navarro didn't try to port the block to perfection. He simply brute forced the solution. He pioneered the application of a GMC3 71 supercharger on a roadster. This was a Roots-type blower designed for industrial diesel engines, essentially a massive air pump. By bolting this to the top of the Flathead, he physically forced the air-fuel mixture through those restrictive side valve ports. The engine didn't have a choice. It was going to breathe whether it wanted to or not. But looking at the induction setup reveals the true level of detail here. You will see 4 Stromberg 97 carburetors, but they aren't sitting upright. They are turned sideways, mounted back to back directly on top of the blower case. This wasn't an aesthetic choice. It was a packaging necessity to feed the massive volume of fuel required by the blower. And the fuel itself was the next critical component of the system. Navarro stopped running gasoline. He tuned this entire array for pure methanol. Methanol was the secret weapon against the Flathead's overheating issues. It has a high latent heat of vaporization, which means that as it changes from liquid to gas inside the intake, it absorbs a tremendous amount of heat. Navarro was using the fuel as a chemical intercooler, chilling the intake charge and preventing the engine from melting down under the 15 pounds of boost pressure he was throwing at it. Once he had the power, he had to keep the engine from flying apart. This is where Navarro defied the common hot rod wisdom of there is no replacement for displacement. He actually went smaller. He took a 1941 engine block and de-stroked it, reducing the displacement to just 176 cubic inches. To the uneducated observer, Giving up cubic inches seems like giving up power, but Navarro understood that horsepower is a function of torque times RPM. To beat the Cadillacs, he needed to spin the engine faster than they could go. A long stroke creates high piston speeds and massive inertia forces that tear connecting rods in half. By shortening the stroke, he reduced that piston velocity, allowing the engine to live at RPMs that would turn a stock flathead into shrapnel. He supported this high RPM architecture with a custom-machined flat-plane crankshaft. Almost every American V8 you have ever heard uses a cross-plane crank, which relies on heavy counterweights to smooth out vibrations. A flat-plane crank is lighter, inherently unbalanced, and vibrates like a jackhammer, but it is much lighter, and crucially, it improves exhaust scavenging, pulling spent gases out of the cylinder more efficiently. Navarro didn't care about driver comfort or vibration. He cared about reducing rotational mass to let that engine scream. It is only when the entire package is engineered to work together that the camshaft becomes relevant. While the cam profile plays a major role, the critical factor is not just the shape of the metal, but the precise mechanical action used to control the valves. He used adjustable mechanical lifters. The new Cadillacs were using hydraulic lifters, which are self-adjusting and quiet but prone to pumping up and floating the valves at high speeds. Navarro's solid mechanical lifters were loud and required constant adjustment, but they were precise. They ensured that when the Winfield cam said open, the valve opened, and when it said close, it closed, even at 6,000 RPM. A victory of mechanical violence. On paper, this matchup was absolutely ridiculous. If you were a betting man in 1949 and you looked at the spec sheets, you would have bet the farm on the General Motors product. In the red corner, you had the brand new 1949 Cadillac V8. This wasn't just a new engine, it was a revolution. It was a 331 cubic inch masterpiece of modern engineering. It featured cross-flow cylinder heads, overhead valves, a sturdy bottom end, and it made 160 horsepower right off the showroom floor. It was the future. In the blue corner, you had Barney Navarro's Flathead Ford. It was an ancient design based on architecture from the early 30s. And thanks to Navarro's radical de-stroking process, it displaced only 176 cubic inches. That is barely half the displacement of the Cadillac. It was a tiny, archaic lump of iron trying to fight a spaceship. In any normal universe, the Cadillac eats the Ford for lunch and doesn't even burp. But racing does not happen on paper. Racing happens in the real world, where physics exposes the compromises made by factory engineers. And the Cadillac 331, for all its brilliance, had a glass jaw. You have to remember what a Cadillac was in 1949. It wasn't a race car. It was a luxury barge designed to transport doctors, lawyers, and bank presidents in absolute silence and comfort. To achieve that level of refinement, General Motors engineers made a very specific choice. They equipped the engine with hydraulic valve lifters. For a street car, hydraulic lifters are brilliant. They use the engine's oil pressure to automatically take up the slack in the valve train. That means zero maintenance, zero lash adjustment, and crucially, zero noise. They are silent and smooth. But hydraulic lifters have a fatal flaw when you try to treat them like race parts. They have mass, they are heavy, and they rely on fluid dynamics to function. When you try to spin the engine fast, the oil inside the lifter cannot react quickly enough to the rapid movements of the camshaft. The heavy mechanism gains too much momentum. At around 4,500 RPM, the Cadillac engine hit a wall. The physics of the hydraulic lifter would fail. They would pump up, meaning they would expand and refuse to collapse, holding the valves open when they were supposed to be closed. We call this valve float. It is a catastrophic loss of efficiency. Imagine the piston rushing up toward the cylinder head at 60 miles per hour, trying to compress the fuel-air mixture, but the valve is still dangling open because the heavy hydraulic lifter couldn't get out of the way fast enough. All your compression bleeds out. The engine sputters, wheezes, and power falls off a cliff. The Cadillac was a sprinter that ran out of breath halfway down the track. Its top speed was chemically limited by its own valve train to roughly 100 miles per hour. It was a lion with a muzzle. Barney Navarro looked at that luxury-focused engineering and saw a massive tactical opening. He realized that while the Cadillac had the displacement and the airflow, it didn't have the RPM potential. It was a tractor engine in a tuxedo. Navarro's entire system, the de-stroked crankshaft, the lightened reciprocating assembly, and crucially those solid mechanical lifters, was built to exploit this specific RPM gap. Navarro didn't care about silence. He didn't care about driver comfort. He installed solid, adjustable mechanical lifters. These are dumb, simple pieces of hardened steel. They don't self-adjust. They don't use oil pressure. They rattle and clatter and sound like a sewing machine falling down a staircase. But they are precise. When the aggressive lobes of that Winfield racing cam kicked the lifter, the valve opened. When the cam profile dropped, the valve closed. It didn't matter if the engine was spinning at 2,000 RPM or 6,000 RPM. The mechanical valve train did exactly what it was told. While the massive Cadillac V8 was floating its valves and choking at 4,500 RPM, Navarro's tiny Flathead was just clearing its throat. Because he had de-stroked the engine to 176 cubic inches, he had significantly reduced the piston speed and the inertia loads on the connecting rods. He built a buzzer. He traded torque for velocity. He accepted that he had a small engine, so he spun it to speeds that the big OHV engines simply could not structurally handle without destroying themselves. The results on the Salt were absolute and undeniable. In 1950, Navarro's Roadster didn't just inch past the century mark. It screamed all the way to 146 miles per hour. His customer, Harold Daig, set a Class C Roadster record of 143.19 miles per hour using Navarro's equipment. Think about the violence of that speed for a moment. 146 miles per hour in 1950. He took an engine with half the displacement of the Cadillac, an engine with a fundamentally inferior airflow design, and he made it go 46% faster than the state-of-the-art competition. This was the definition of asymmetric warfare. Navarro realized that horsepower is just a number derived from torque, multiplied by RPM. If he couldn't make the torque of the big Cadillac because of his small displacement, he would beat them with RPM. He exploited the luxury compromise of the hydraulic lifter to humiliate the factory engineers. Now, history tells us that the overhead valve revolution was inevitable. Eventually, the aftermarket caught up, giving the Cadillacs the solid lifters and springs they needed to unlock their massive potential. But that reality doesn't diminish Navarro's achievement. It actually elevates it. For that beautiful fleeting window in the early 1950s, Barney Navarro forced the future to wait. He took a design that was supposed to be extinct, and, through sheer intellectual willpower, made it the fastest thing on the Salt. It stands as a permanent reminder that while displacement is great, engineering brilliance is the ultimate equalizer. The polymath of high pressure. The story of Barney Navarro does not end when the Flathead V8 finally succumbed to the overhead valve invasion. For most hot rodders, the Flathead was the end of the line, but for Navarro, it was merely a case study in applied physics. The lessons he learned trying to keep that archaic engine from exploding under 15 pounds of boost taught him everything he needed to know about the future of performance. He realized early on that while a mechanical supercharger was effective, it was inefficient because it dragged on the crankshaft. He looked at the wasted heat energy exiting the exhaust pipe and recognized it for what it was: free horsepower. Long before turbocharging was a common word in the automotive lexicon, Navarro was preaching the gospel of exhaust-driven induction. In January 1962, he published a landmark article in Hot Rod magazine titled Hot Horsepower, where he broke down the thermodynamics of using waste heat to spin a compressor, drawing a direct line from World War II bomber engines to streetcars. He didn't just write about it, he built it. He took an A-Research turbocharger designed for a diesel industrial engine and fitted it to a Chevrolet Corvair. This was years before Chevrolet released their own turbocharged Corsa model. He was engineering the future in his garage while the OEMs were still in the boardroom. His obsession with efficiency culminated in one of the most audacious racing projects of the 1960s. He decided to attack the Indianapolis 500, but he didn't do it with a Ford or an Offenhauser. He showed up with a customized AMC Rambler Inline 6. This was a 199 cubic inch commuter engine, the kind of thing you would find in a librarian's sedan. Navarro fitted it with a complex twin-turbo setup and a mechanical fuel injection system of his own design. He managed to extract over 600 horsepower from that grocery getter. While the car ultimately failed to qualify due to chassis handling issues, the engine itself was a masterpiece of high-pressure engineering that terrified the establishment. But the true measure of Navarro's genius is that his understanding of fluid dynamics wasn't limited to gasoline and oil. He viewed the world as a series of mechanical problems waiting to be solved. The same mind that figured out how to equalize fuel distribution in a flathead intake manifold later applied those principles to the medical field. Navarro designed and built a sophisticated heart-lung machine used by Kaiser hospitals. He effectively treated the human circulatory system with the same reverence for pressure and flow as he did a race engine. He also invented commercially successful concrete cutting saws, proving that his engineering principles were universal. This is why his legacy endures. He wasn't just a mechanic trying to go fast. He was a polymath who understood that the laws of physics are the same whether you are cutting concrete, pumping blood, or outrunning a Cadillac on a dry lake bed. The triumph of engineering rigor. We started this story by questioning the idea of a simple cam trick. But if you have learned anything over the last few minutes, it is that there is no such thing as magic in mechanics. Barney Navarro's victory over the Cadillac 5.8 was not a sleight of hand. It was a triumph of systematic engineering rigor. He took a Flathead Ford, an engine that was structurally obsolete, thermally inefficient, and unable to breathe, and he forced it to perform through sheer intellectual force. It required the integration of a diesel supercharger, an industrial flat-plane crankshaft, exotic alcohol fuel, and a de-stroked rotating assembly just to get the platform to survive. The Winfield cam was merely the final piece of the puzzle that allowed him to exploit the one weakness the Cadillac had. He found the gap between luxury engineering and racing reality, the hydraulic lifter, and he drove a methanol-fueled roadster right through it. This is the enduring lesson of Barney Navarro. Fast cars are not built by opening a catalog and buying the most expensive parts. They are built by understanding the physics of failure. Navarro proved that an inferior architecture, when refined by a superior engineer, can temporarily defy the march of progress. The overhead valve revolution eventually won the war, of course. Once the factory engines got mechanical lifters and better springs, the Flathead was finished. But for a brief, glorious moment in the 1950s, a machinist from Glendale made a Flathead fly.